Good afternoon to everyone, and welcome to this short course on Feynman Diagrams given by Dr. Helio da Motta. Dr. Helio da Motta is a researcher in the Brazilian Center for Physics Research in Rio de Janeiro, Brazil. Um, he has been working on high energy physics in the experimental area of high energy physics for probably 2 decades, Helio? Probably more than that.
Yes, maybe more than that. Yes.
Probably more than that, yeah. So this short course is an event organized by the Faculty of Science of the National University of Engineering as part of the XIX Meeting of Physics. Well, as you probably know, well, we got some issue with the capacity, so we cannot attend to everyone. So for that reason, this course will be also streamed on YouTube. So the link of this short course will be on the website. Okay, so I'm pretty sure that you all will enjoy this course. So Helio, you're up, please.
Hello, can you hear me well?
Yes.
Okay. So I want to thank the organizers for the opportunity to give this very short course covering some subjects that they are very important for high energy physics. And what I aim to do in this course is to make some short presentation of the high energy particle physics, but giving some attention to Feynman diagrams. The idea is that at the end, we will be able to make a simple calculation of a simple Feynman diagram, at least to understand the process. It's a very complex process, and of course, a short course in only 1 week, 10 hours a week, is not enough to cover everything. So I try to concentrate in a few subjects. So, of course, there are too many people attending, so I cannot ask everybody to make an introduction itself. As Professor Castromonte said, I have been working this business for quite some time. And I had the opportunity to go to Lima in person a few years ago, before all this mess started. But this year, we are going to have this course through the internet, what I think would be okay. So let me start sharing my screen to make a presentation. Okay. Can you see my screen?
Yes.
Okay. Okay. Today I'm going to make a very short introduction. Okay, so I have to present some basic principles, and the following days we're going to concentrate in a few aspects of physics, of Feynman diagrams, until we can end with some simple calculations. So this is the introduction to particle physics. I mean, of course, I think it's wrong. I think it's not the 20th meeting. I think it's the 19th. But anyway, I'll fix that later. Okay, let's start with some basics. I'm trying to speak in English in a very soft and slow pace to make it easier for people to understand, okay? I am going to spare you from the embarrassment of listening to my Spanish. So, what you do in physics, high energy physics, is what you call the standard model. It's basically the theory we have at the present to describe the interaction of particles that make our universe. So basically, what you have in this standard model is that you have what's called the fundamental constituents. So those are the elementary particles. And what we believe, and we are pretty much sure about, is that everything in the universe is made from those particles. Together with those particles, we have interactions. The particles by itself would be of no importance if they could not interact. So the interaction between the particles are mediated by what we call forces. So there are forces between particles. To have an idea, so we all know about atoms. And the atoms are bound states of electrons, protons, and neutrons. So if you have protons and neutrons in the nucleus, and then you have electrons around the nucleus, that makes us an atom. It's a bound state because all these particles are kept together. And the reason why they're kept together And because they interact, they exchange some information that allows them to be together. So the electrons are bound to the nucleus by what's called electrostatic attraction. Basically, we all know about that Coulomb law that regulates attraction between particles. If you have a particle with a positive charge, the particle with negative charge, there is a force between them. And so this basically is the force that keeps electrons together with the nucleus forming an atom. And this would be the subject of what we call QED, so quantum electrodynamics. And this is something we give some attention because the Feynman diagram that I plan on resolving with you is be a Feynman diagram of a simple electromagnetic interaction between electrons. Then we have the nucleus. The nucleus is inside the very center of the atom, and there we have protons and neutrons that are also bound together. As we know, protons have a positive charge. And so we have a nucleus of an atom with many protons, and so there should be a very strong repulsion. They should really explode because too many protons with positive charge, if you just apply the traditionally classical Coulomb law, the force taking them apart is very high. They should not be there. However, they stay together. That means that there must be something stronger than an electromagnetic interaction that allows all these particles to stay together, the part of the fact that the electromagnetic interaction would just send them apart, exploding. This is what we call strong nuclear force. It's not a very original name, but that's the name we have, the strong force keeping them together, much stronger than electromagnetic. And this is subject of what we call QCDs, quantum chromodynamics. We are not going to give much attention to this, just to understand a little bit how it works. And then we have what we call a beta decay that's regulated by the weak force. The beta decay is a process where a particle basically decay in another particle. So you have a particle with some mass, some level of energy, and they decay into a much lighter particle. Like, for instance, we have a neutron that's inside the nucleus, and the neutron may decay into a proton. That's a lighter particle. So the process that mediates this process is called a weak process, and we have a weak force. The name is not very original, again, but it means that this interaction is very weak compared to the others. So basically, what we have in the universe is electrons. This is the symbol for the electrons, okay? Okay, the electron. Okay, electron. We have protons, you have neutrons, and you have what we call neutrinos. Okay? This is basically to have the universe. However, there are many other particles, and at some point you must understand what role all the other particles play in the universe. So at the end, I should mention briefly gravitation. Gravitation is the other interaction of nature. We have four of them: the electromagnetic interaction, we have the strong interaction, we have the weak interaction, and finally we have gravitation. Gravitation is very weak, but really very weak. Much weaker than all the other interactions, to the point that for particle physics, it's not irrelevant, at least has not been relevant. However, what happens with gravitation is that the gravitation is a long-range interaction, so in principle, a body will be able to interact with another body no matter how far away they are. And also, it's a kind of interaction that adds up. So if you take our planet, Earth, our planet Earth has a huge amount of matter. But at the end, all this is neutral because we have the same number of protons as electrons. So there is no electric charge in the total. However, the mass of all these particles, they add up. And then we end up with a huge amount of mass, and that's why we can perceive gravity. But if you go to the domain of particles, we only have electrons, we only have protons, and we have neutrinos in the small particles. The mass is so small that the gravitational interaction between them, although in principle may exist, is not important. So gravitation is not part of our study. We really do not care much about gravitation. Okay, but how do we deal with all this stuff? Okay? This plot here, this diagram here, is just to give you some idea what happens. As we increase the energy of the process, we are able to go deeper and deeper into the atom that makes the matter. For instance, if you increase the energy, and here we have the increase of energy goes this way, increasing. So at the lower energy, we are pretty much able only to deal with the atom themselves. But as we increase the energy, it's pretty much like what you have with a telescope or a microscope. As we stronger the microscope, the stronger the telescope, further we can see. With the microscope, we have more power. You can see deeper and deeper in the cells and inside the cells. Here in the case, what we have to do, if you want to really look into the matter, into nucleus, you have more energy. So we don't need much energy for atoms. Not much energy. But if you want to really look inside of the nuclei, the nuclei have protons and have neutrons. Then we need much more energy. Understand from the point of view of quantum physics that more energy means that the wavelength is shorter. Okay, and so you have more energy. It means that you have a shorter wavelength, and this shorter wavelength then it allows us to go deeper and deeper and deeper. So if you really want to go inside the nucleus, inside the proton, the nucleus, that you have what you call quarks, then you need even more and more energy, and so on. So basically, that's our idea. More energy, you have more details. Yeah? And what we have found some time ago is that protons and neutrons, they are not fundamental particles. But fundamental particle, from our point of view, is a particle that exists by itself. It does not have any constituents. An atom is not a fundamental particle because atoms have electrons, they have protons, they have neutrons. Electrons, by itself, by the other side, are fundamental particles. They have no constituent. Nothing gets together to make an electron. The nucleus of a particle has protons and neutrons, so nucleus is also not the fundamental. And up to a few decades ago, our understanding is that protons and neutrons could be fundamental particles. But this is also not true. Protons and neutrons are bound states of what we call quarks. So, as we know today, a proton is made of 3 quarks, and the neutron is also made of 3 quarks. The quarks are not necessarily the same, and the way they're put together can provide different levels of energy. So a proton, as we show here, has 2 quarks, U, and 1 quark, D. I'm going to talk about the quark in a few minutes. So the names are not as interesting as electron and proton, but basically the combination of different quarks will make a proton, or will make a neutron, or many other particles. So the quarks, as far as we know, are fundamental particles because the quarks have nothing inside them. At least that's what we believe now. Now, what about generations? What we call generation. Okay, as I said at the beginning, we would be very happy having only electrons, protons, neutrons, and maybe what we call neutrinos. But that's not how things are. As people study more and more high-energy physics, many experiments from last century to now, people start finding other particles. And it was observed that there were particles that looked a lot like an electron, except that those particles were much heavier than the electron. So this particle that we call a muon is pretty much like a fat electron to higher mass. And then it was observed that the same thing that happened to electrons happened to other particles. So the quarks that we see here, the quarks that made up together to make a proton and a neutron, are quarks of the type U and quark D. So in principle, all we would need was quarks U and quark D, so we can make protons and neutrons. We would be very happy with that. However, that's not what we observed. So basically, we observed that there were several generations of, I would say, fundamental particles. So they come in groups. The first generation, the second generation, the third generation. Basically, the second generation is a replica of the first generation, but with a much higher mass. And then the third generation is a replica of the second generation, but with a much higher mass. What ends at that in nature, things have a tendency to go to the lowest level of energy. So this first level, the first generation, is pretty much the stable level. The particles that are in the second generation eventually will decay into the first generation, and that's where things stop. No? So basically, well, electron, mu, this is wrong. This should be what we call a tau, is another particle. Electron, mu, and taus are identical, except for the mass. We cannot distinguish them by any other property. They have the same electric charge. Everything you find in one, you find in the other, but the mass is different. In fact, the mass of the mu is much higher than the mass of the electron. The mass of the tau even higher. And so far, we have evidence, both experimental and theoretical evidence, that exists only 3 generations. So 3 different groups of this fundamental particle, the common group. So if this is true, and we are pretty much sure that's how things work, we have the universe has 12 fundamental spin half particles. The spin, as if you can understand this way, the spin is like an intrinsic rotation of the particle. Is like if the particle has an intrinsic angular momentum, if you understand this way. It's a quantum universe. So we have 12 fundamental particles. So we have the quarks. We have 6 quarks, U, D, S, B, and TC. 6. We have the electrons, the muon, the taus, and we have all these anti-particles of all these things. So the dynamics that we have to deal with that in place the antiparticle. Antiparticles was something that was first considered from a theoretical point of view, from this guy here, Dirac, and eventually experimentally was found the antiparticle is pretty much like the particle, but having everything reversed. So the electron has a negative charge, but the anti-electron has a positive charge. Everything that electron has, the anti-electron has the other way around. And this goes for all particles. So they pretty much would double the number of particles this way. This table here makes a very brief description of the particles. So we have what we call leptons and what we call quarks. There are 2 different groups. And here we have the 3 generations. So in the first generation, we have electron and neutrinos. Okay? Here is the charge. The electron has a charge of -1, neutrino has no charge. And the mass of the electron, you see, electron has a very small mass, 0.00005. Very small. The other group is what we call quarks. Remember, quarks are those particles that end up making protons and neutrons. No, they are part of it. So we have also 3 generations. The difference from the first generation for the second generation, if you see the second generation, you have a mu, here, mu, pretty much like an electron. But look, the mass of the muon is much, much, much higher than the mass of the electron itself. About 200 times more. So the muon was 200 times heavier than the electron. Very strange. And here, when we go to the quarks, the 2 quarks from the first generation, we call quark U and quark D. No? What you should pay attention to quarks is that they do not have an integer number of charge. That charge is a fraction of the 1, the -1. And here we have -1/3. So when the quarks get together, they do it in such a way that the final particle, like a proton, will either have a charge of +1, 0, or -1. For instance, if you get together 2 up quarks, in one d quark, we have 2/3, 2/3, and -1/3. So after, okay, I continue from here. Okay. So what you have about quarks I speak a little bit faster to compensate for the time now, okay? So we have a force, but the gravitation is not of our concern. We don't care about that. So the weak force, the interaction, act on all particles. The electromagnetic act only charge the particles. Strong interact only with quarks. Quarks have what we call a color charge. And the quarks are never free. They are always together, always bound in the hadron state. So what happens, basically, is that we have the families. So the first generation here is the first generation. We have the second generation and the third generation. Okay? And here we see how they belong. So quarks, all kinds of quarks, they can interact through strong interaction, electromagnetic interaction, and the weak interaction. They fuel all of them. Although the strong interaction is much stronger, as the name suggests, what happens if in any process they may interact strong or electromagnetically, then the strong will prevail. When it comes to leptons, and we have charged leptons, the electron, mu, and tau, they don't have what we call the strong charge, the color charge. So, but they can interact electromagnetic and weakly. And finally, we have the other leptons that have no charge, the neutrinos. Those interact only through the weak interaction. So neutrinos, if neutrinos are involved, the interaction is a weak interaction. So what I was talking now when I got the call from Cesar is that how that happens, how things act at a distance, how a particle knows about the other. Newton was concerned with that. He was not happy with the idea that the Earth and the Moon would interact without touching. So there came the idea of a field that also does not explain much, just describe how it happens. What is happening nowadays is the following. If you have one electron and a second electron is placed about, say, 1 meter from that electron, we know there is a force between two electrons. But how that happens? What happens is that the electrons change, they send an information to each other. They exchange the information. So this exchange tells the other one, I'm here, or I have a charge of minus one. What can do about that? So basically, and this is the part that comes with the Feynman diagram. Let me start from zero here. Okay, this is what we call a Feynman diagram. A Feynman diagram describes a process. Okay, Feynman diagram. Feynman diagram. I suggest, it says that to avoid any problem like that, every minute or so you just send me a cue saying that you can see me or anything. Okay? So okay. The idea is that we have, in this case here, two electrons. I would say this is electron 1, this is electron 2. Okay? And here we have time. Okay? So what happens? This electron 1, at certain point here, sends a photon. And here, emits, sends, receives. So the electron 1 sends a photon, and the electron 2 receives the photon. So they exchange some information. Because together with this photon, they send some momentum, and they send the energy. So that's so if the electron is sending a photon with some momentum energy, the electron loses that energy and loses that momentum. And the other electron receives that energy and that momentum. So energy and momentum are conserved, and they know about each other, and that's how they interact. Of course, could be the other way around. Maybe the electron 2 also sends a photon, and the electron 2 receives a photon. Okay? No, so there is a time difference between sending and receiving. So both happen. So this is a Feynman diagram that describes the process. The lines here, this just shows that two electrons are interacting. Does not mean that this has not to do with the direction of the electron. Yeah? So So these particles that exchange, these electrons, are the real particles, the particles that you can really observe in a lab. But the particle that is exchanged is called a virtual particle. And this exchanged particle, this is the one that carries the force. Okay? This is the one that allows one particle to interact with the other. So what happens if you try, if you have, say, a neutrino has no electric charge. The neutrino is blind to electromagnetic. So even if an electron is close to a neutrino, and this electron is going to send photons, the neutrino is not going to receive that photon because not see. So the neutrino will not interact through the electromagnetic interaction. So the electromagnetic interaction exchanged what we call a photon. The strong interaction sends another particle that we call a gluon. I have some diagrams about that. And the weak interaction is more complicated, sends two kinds of particles. The process is the same. They send a particle and they receive. In the case of the strong interaction, for instance, one quark will send a gluon, and the other quark will receive that gluon. So they exchange some information through a gluon. In the case of the weak interaction, a particle, like say an electron, will send a W, and the other particle will receive that W, and so they interact this way. In the weak interaction, there are two kinds of particles. They also can send what's called a Z or a W. So a neutrino can send a Z0, and then an electron receives that Z0. So the electron and the neutrino interact through the weak interaction. Again, if you have a quark and we have electron, the quark may send the gluons, okay, but the electron does not see the gluons. But the quark also sends the photons because the quark has electromagnetic, has a charge, and then the electron can perceive. So the electron will perceive only the electric charge of the quark, not the strong charge of the quark. And the neutrino will not notice. The quark is sending gluons, the quark is sending photons, the quark is sending Z's. Neutrino cannot see the photons, neutrinos cannot see the gluons, but neutrinos can perceive the Z. So the neutrino will respond to the interaction with the quark, but only through the weak interaction. Okay? So just to have an idea how strong or weak they are, can you still hear me?
Yes, everything's okay.
So how the forces relate to each other. So here we have the strong force, and I give the strong force a strength of 1 to compare. Boson is the general name of the exchanged particle. So in the case of strong interaction, the particle that they exchange is called the gluon, okay? And the force has a strength of 1. If you go to the next interaction, that's electromagnetism, for instance. See, the electromagnetism is 10 to minus 3, so 1,000 times weaker than the strong force, much, much weaker. It means that you have two particles that are able to interact through the strong force and through the electromagnetism. Like, for instance, two quarks. Two quarks may interact both ways, but the interaction the two quarks feel based on the strong interaction is 1,000 times stronger than the one from the electromagnetism, the one due to their electric charge. The next one, that's the weak, well, it's even weaker, 10 to minus 8. 10 to minus 8 is how many millions? Oh my God, 10 millions? No, 10,000 times, right? 100,000 times, basically. So the weak so you have a quark, two quarks that may interact with each other through all the two ways, the strong electromagnetic and the weak. The exchange they perform through the weak interaction is much 10 to minus 8 times weaker than the strong. So the strong will prevail. It doesn't mean that the weak interaction is not important. On the contrary, the weak interaction is very important, as we're going to see soon. Because the weak interaction basically is the one that allows particles to change what we call flavor. That's what allows things como neutron decay into a proton, and at the end is what allows the sun and the other star produce all the energy that we use. So the weak interaction is very important. Just because it's weak doesn't mean that it has no meaning at all. And then just to have an idea, here's gravity that we don't care about, and then see 10 to minus 37. This is very weak. So we do not even consider. But in any way, the boson, the electromagnetism exchange photons. We can exchange W or Z, and the gravity may be graviton. Maybe because people have not been able to make a theory describing this. So we don't care about gravity anyway. So this is good. Here we have an idea of the mass of the things. For instance, the gluon and the photon have no mass, but the W and Z have a very high mass, about 8 and 9 to 1. This also affects the way the theory works, but we are not considering this now at the moment. So now let's see how these interactions happen. Okay. Then how is the nature of the interaction? What are the properties of the boson? The boson is the one that makes the connection between two particles when they interact. So here we have a representation, a basic representation of the interaction. Electromagnetism. What we have in electromagnetism, here I have electron, but I could have a muon. I could have even a quark, because a quark also has charge electron. But I want to call attention here to electron, because if we, as I said before, if we have electromagnetism and at the same time we have also strong interaction, the strong will prevail. But in this case, I show the electron, basically electromagnetic prevail. So what you have basically is this vertex here. So at some point, the electron receives or sends a photon. So all particles never change the flavor. So all particles that have charge are able to send and to receive photons. And they do not change. So they not change means that an electron sends a photon and it's still an electron. He does not lose whatever makes it an electron. It loses energy, of course, and momentum, but this will be transferred to the other particle. Okay? Then we have the strong interactions here. It's pretty much the same thing, but in the case we have a quark, and the quark at some point is able to send or receive a gluon. Okay? Notice that the diagrams are of the same kind. What changes is that here we have a gluon, and here we have a photon. But the idea is the same. They exchange some information through this boson. In the case, only quarks. Quarks are the only particles that have the charge that produce the strong interaction. They also never change the flavor. Means that when a quark sends or receives a gluon, it's still a quark. The same quark. If you saw before, you have quarks U, quark D, S and C, T and B. Okay. Each one of them can send a gluon and can receive a gluon, and they don't change. When a quark C receives a gluon, he may get some more energy, gets more momentum, but it's still a quark C. When a quark C sends a gluon, okay, together with the gluon, it will lose some energy, some momentum, but will still be a quark C. It doesn't change. Okay? And then finally, we have the weak interaction. Well, the weak interaction is different. Again, we have the same kind of Feynman diagram, basically. In the case, I'm showing an electron in neutrinos. Now, the weak interaction can exchange W's we have 2, and Z0. Z0 has no charge, okay? But the W has electric charge. What means that when an electron, at this point here, sends W minus, for instance, together with the W minus goes the electric charge. So it's like the electron loses the charge, electric charge, then it's no longer an electron. Now it's a neutrino. The electron lost its charge, becomes what's called a neutrino. The charge does not disappear because the electric charge goes with the W that's here. Okay? Of course, the electron here sends an electron, but it's also possible that it receives, né? What's the same? So important thing is when the particle exchanges a W, this particle changes its electric charge, and then it's no longer what it was before. But the other part of the electron, the weak interaction, what is it here? The other part of the weak interaction is also possible to send a Z. The Z has no electric charge. That's what the 0 here means. Then when it sends or receives a Z, the charge doesn't change. So when a neutrino sends or receives, the charge doesn't change. So it's still a neutrino. Neutrino, on the other side, if the neutrino gets a W, it gets electric charge and then becomes an electron, for instance. So, of course, the electron may also exchange a Z because it also works with weak interaction. But if the electron exchanges a Z, it's still electron, does not change. So the important thing here is that all fermions, they always change flavor. So the weak interaction with a W, that's called a charged current interaction, changes flavor. Changes flavor means that if you are electron, now we're not an electron. We're going to be neutrino. If you are here, if you are here, note there is a difference in charge. Okay, and the quark C and the quark S, there is a difference of charge, 1. So if this quark receives, or the dependent oscillation sends a W, it loses or gets electric charge equal to 1. Then it goes from -1 to plus 2/3. So if there was a strange quark, a quark S, now it's going to be a quark C. So the weak interaction, when by exchanging that, is able to change the flavor of the part. The electron may turn into neutrino, and a quark T may become a quark B, a quark C may become a quark S, and so forth. So they are very important in this kind of process that happens a lot in nature. So, how it works is the weak interaction coupling. So how they put together things. Here we have the leptons. Leptons, again, are the electrons, the muon, the tau, and the neutrinos. Each one has a neutrino. So it's a neutrino is a particle with very, 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 very low mass. Okay, no electric charge. And they come associated with the electron, the muon, and the tau. And here we have the quarks. What we are showing here in these groups are these differences. Aqui tem. There is a difference of electric charge of 1 between U and D, U and S, U and B, all them. What it means that by exchanging, by sending or receiving a W plus a W, can you hear me? I got no sign. Hello? Lost again?
No, Helio.
Oh.
It will be fine.
Okay. So by exchanging a W, C and S may change place. If you have a C, you may have an S, a S, a C, and so forth. So those are the pairs that can change by this weak interaction. So this change weak interaction change flavor through exchanging, and this is very important. Okay, so CC, what we call CC, is charged current. Charged current because the W is charged. Okay, and the other one, when we exchange a Z, nothing happens. We call it a neutral current. And in this case, S and U, they are quarks. They may receive or send Z, and they do not change flavor. They're still what they were before. Now, what about the intensity of the interactions? Well, the interactions do not have all the same intensity. And the intensity is defined by a coupling. There's a constant that we call, in general terms, we call it a Z, a G. Okay? Basically, what this coupling constant gives is the probability of a fermion to emit or to absorb the interaction boson. Fermion is the general name for the quarks, and electrons, muons, they all call it fermion. So, there is if you take a quark, if you take, for instance, an electron is able to send and receive photons, W's and Z, because electrons interact electromagnetically and by weak interaction. So the probability of that happens is basically dependent on this constant G. So the probability of sending and receiving a photon, for instance, for an electron, is much, much higher than the probability of sending or receiving a W or a Z. That's basically what defines the intensity of the interaction. So as high as this constant, higher the probability of a fermion to emit or to absorb. So higher the probability of interaction to happen. So basically what we have to do here is to have two vertices. Here what we have here a fermion, could be a quark or whatever, could be a quark, electron, and here we have another fermion, not necessarily the same kind. And here they exchange something. That's what the boson that's exchanged. It's by exchanging some information, it's by exchanging a boson that the two particles are able to interact. So they will exchange a photon, a gluon, a Z, a W, whatever, depending on the interaction. So if they can exchange gluon, with much higher probability of exchanging a photon, because the strong interaction is much, much, much stronger. So in the case when you have two particles interact, we have these two vertices. One that's the particle 1, and that's sending, and the one the particle 2 that is receiving. It happens both ways. So you always have two vertices if two particles interact. So, and then there is a value that we call m, that's proportional to the square of this interaction here. Okay? So the probability of interaction is proportional, basically, to this. That means that for the case of the electromagnetic, this alpha, that is basically what it measures, is to the order of 1 to, I think you saw this number when you studied physics, okay? So for the electromagnetic is 1, so 137. For the weak interaction is 1 over 30, and for this strong is about 1. Then what happens? Since we have two vertices, we will have for the electromagnetic interaction 1 sobre 137 squared, because we have two of them. It gives a very small number. Then let's look here at Feynman diagram to see how this will work. Important to understand that a Feynman diagram represents the transition between states. Okay, it has nothing to do with the direction of movement, not at all. And they represent all possible time orders in which a process may occur. For instance, here, we call it particle A and particle B. That's the initial state. So at the beginning of the process, we have two particles, particle A, particle B. Doesn't matter. One electron in the positive, one electron in the quark, there are two particles. Here, at some point, they exchange. So they exchange a photon, a gluon, a download, whatever. So by exchanging this, they are interacting. One particle sends, the other receives. And in fact, we have two possibilities. We may have the particle here, the particle A sends, and the B receives. Or the particle B sends, and the particle A receives. Notice here that I say that the particle A exchange an X, or whatever, and then is now particle C. And the particle B is now particle D. So they could be the same. So this is a very general representation of what may happen. We know, for instance, if A is an electron, and they exchange a photon, C is also an electron. But C is an electron, if they exchange a W, then C will be a neutrino. So this is a general representation of how things happen. Then what you have to do is to sum all of them. So these two diagrams is not that, I'm not saying that either we have this or that. That's not what happens. So when you describe a process, let's say that you have a series of a Taylor series. In a Taylor series, we have many terms with different order. X squared, X third, fourth, fifth, and so forth. So all the terms represent the process. Okay, all of them have a participation. What happens is that some of them may have a much higher participation than others. So is that to really consider, to really work with this process, to really make a calculation, we must consider both the possibilities. Both possibilities is the one that's going to give the number that somehow is related to the process. Remember, if you have to process, and you get the Feynman diagram, and you calculate the number associated to the Feynman diagram, that's what I plan to do by Wednesday or maybe probably Thursday. Then, if you have to process, one gives a number that say 35, the other one gives a number that say 20, means that the one at 25 is more intense, is more likely to occur, will be more dominant than the other one. Then I have to sum all the diagrams to really know what's happening to the process. So, Feynman diagrams, well, in fact, it is something important to understand, is that we have an infinite number of Feynman diagrams for each process, not just one. Here I give an example. A very simple example. I have an example of an electron interacting with another electron. So here we have two electrons resulting in two electrons. They just exchange a gamma here. Okay? But also, I may represent this in a more complicated way. I may say that this electron here sends or exchange gamma. Okay, and then exchange a gamma and continues to be an electron because it does not change the flavor. And then here, exchange again. So at the end, because all we can see is this. We don't see what's inside. Huh? We do not see. We don't see here. We only see two electrons resulting in two electrons. But inside, they may have just an exchange of one photon, or here, the exchange of two photons to different instant moments, or here is even worse, because here I have a diagram that's exchange, 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 exchange. No, again, I only see outside. So at the end, I have the same thing. However, here in this case, I have two vertices. Okay? So that the amplitude that represents the Feynman diagram will be proportional to alpha squared. Alpha in the case is the order 1/137. In this case, I have four vertices. So the m squared is proportional to alpha, the fourth power, and here to the 60th power. So what happens is that alpha is very small, then the fourth vector diagram, this one, is suppressed by a factor of 10 to 10,000 times. So this diagram here, whatever number a diagram produces, this one you produce a number that's 10 times smaller. And this one here, the other one, is even worse. 10^6 is 1 million times. So if I want to represent it, to make any calculation of this simple process, means two electrons interacting each other, result, although I may get an infinite number of Feynman diagrams, as I see here, only the first one, only this one, only this one will be important, because the other ones will give a contribution 10 times smaller, the other 1 million times smaller. So in practice, the same way as when I have a series of power, I usually take only a few terms of the series to make a calculation. Here, the same will happen. I use, in this case, only the first. Yeah, in some cases, I may need two cases. But fortunately, although I may be able to produce infinite number of Feynman diagrams, usually only the first one, or the first order, will be important for our calculation. Okay? That makes things much easier for you. And when you go to the point of calculating one Feynman diagram, you'll be for this kind here. Because it will be a very simple one to calculate. Even although it's a very simple, the calculation will take some time to do it. Of course, you try to do the other, it will be much more complicated. Now, particle decay. As I said before, a particle may decay in other particles. Most particles decay. What it means decay? The system in nature have a tendency to go to the lowest level of energy. If you get an atom of hydrogen, for instance, we may have this atom of hydrogen. You may excite the atom of hydrogen. So basically, the electron gets more energy, and the electron changes level. The electron goes to another level of energy. And after some time, the electron will go back to the lowest level of energy. And going back, the electron will emit some photons, some light. That's what you see the spectrum of the hydrogen, all the possible decays. In the case of the atom of hydrogen, the difference in level from the lowest level to the first level is small, and we still call it a hydrogen atom. When we deal with particles, we may have a big difference in levels. But in any case, if we have a particle that is a much higher level of energy, and it goes down to the lowest level of energy, we have other particles. So most particles decay. When we talk about fundamental particle, doesn't mean that a particle is stable, ever. No, only very few particles are stable. So although the muon is a fundamental particle, it's a fundamental particle because there are no constituents. The muon has nothing inside of it. So it's a fundamental part. It's not stable. After some time, the muon will decay to a lower level. This lower level is an electron. And in doing so, we saw already, to do that, a W or a Z may be involved in this exchange. It goes to a lower level and emits some energy. So only a few are stable. You have only 12 fundamental particles and 12 antiparticles, but not all of them are stable. No? A particle is stable if it does not decay to any other particle below them. And of course, decay to a particle whose mass is smaller. So a particle decay until a final state of smaller rest mass that can be reached by a process. So if I have a particle with a very high level of energy, this particle will decay to a lowest level, and then decay to a lowest level, until get to the lowest possible level where it stays. So if a particle is in a chain that goes decaying until an electron, once it gets to an electron, stops decaying, because there is nothing below the electron to decay. So decay of fundamental particles happens by the weak charged current. The weak charged current, that one that exchanges at W, is the only one whose vertex allows flavor change. So it's the only one where you can change the flavor. So if there is a kind of decay, a particle changing flavor, means that a weak interaction with W is involved. Let's see an example here. Well, we know the mass of a muon here, mass. A muon is bigger than the mass of an electron. So it means that the muon itself, although it's a lepton, also is a fundamental particle, the muon is pretty much like an electron. However, the muon is like an electron with a much higher mass. So there is a level of energy below the muon, that's the electron. So what happens? Here we have a muon, and here, at some point, exchange a W. W is a weak interaction. By exchange a W, the muon loses its electric charge. So it's no longer a muon, it's neutrino. So the muon loses its electric charge. It turns into a neutrino. Okay? The electric charge does not disappear. The electric charge is here with the W. And then at some point, the W turns itself into an electron. A neutrino, electron neutrino. See, here is the electric charge again. So the electric charge does not disappear. So in this process, the muon loses its electric charge, becomes a neutrino. The W becomes an electron and an antineutrino. And then the process stops because there is nothing below the electron. So here is another example now using the tau. The tau is another lepton. The mass of the tau is much bigger than the mass of the electron. In fact, the mass of the tau is bigger than the mass of the neutrino. Then the process is exactly like the one for neutrino, but in this case, the tau, at this point here, exchange a W. So the tau loses its electric charge and then becomes a neutrino. You can think that the neutrino is a muon neutrino is a muon that loses its charge. A tau neutrino is a tau that loses its charge. A muon neutrino is an electron neutrino is an electron that loses its charge. And then again, this charge is here with the W, and then at some point the W here becomes a muon and an antimuon. It's possible because the mass of the muon is below the mass of the tau. Of course, it will be possible here also to go to an electron. And this point here, once there is a muon, eventually this muon will also decay also. According to the plot, to the Feynman diagram to the left. Okay, so this process always happens until there is no lower level to go. So since the electron is the lightest discharged lepton, eh, no weak process preserves energy. So there is no process that will be able to change the electron and the electron is stable. There is nothing below the electron. So the process stops going in this process. Another example from particle decay. Right, is there a repetition this? Okay, this is repeated for whatever reason. Okay, this so that very soon we're going to talk about the decay, also involving a weak process. Yeah? But at some point there will be a W also. Now, what happens to, we talk about leptons. Let's see how it works with quarks. It was mentioned at some point. Can you still hear me? I hear no feedback.
Yeah, we hear you.
Okay,
Yeah, we are here.
so the quarks are always in bound state. So we don't see a quark flying around. We can see an electron flying. We can see a moon, a neutrino, but not for quarks. Quarks are always bound together. They are restricted to it. So quarks may show up in what we call hadrons. Hadrons are bound states of quarks. And we may have the following situation. We may have a baryon. In a baryon, we have 3 quarks. For instance, we saw that the proton is a combination of 3 quarks. The neutron is a combination of 3 quarks. So a proton and a neutron are baryons. Of course, we may have also an antibaryon. Baryon when you have 3 antiquarks. 3 antiquarks. 3 quarks is a 3q. Here's 3 anti. We have a bar. But also it's possible that you have a combination of a quark. Aqui you have a quark. Here, antiquark. That makes a meson. No? What's important that they arrange in such a way that the same way when you have an atom has electrons and it has protons and neutrons. But electrons and protons have electric charge. But electrons and protons in an atom are in such a way that you have the same number of protons and the electrons. So the net electric charge is 0. There is no electric charge unless you have an ion. Of course, you have no electric charge. With quarks happen something similar. But quarks, we are talking about what we call the strong force charge that we call a color charge. And the quarks always get together in a way that net color charge is neutral, that we call white. So that's what we have here. We have a quark and an antiquark, 2 together. One is going to have one color and the other color. So we never have them separated together. So what happens? What happens is we may have different hadronic states. We saw there before that you have UD, UDD was possible was forming a proton. So a proton was UDD, 1 quark U and 2 quark D. What happens that you may have this UDD together in a much higher level of energy. If that happens, we don't have a proton, but we have another part. The same way is that in an atom, of a hydrogen atom, for instance, if you excite one of the electrons, we still have an atom of hydrogen. The energy is bigger, but it's not very big. In the case of quarks, depending on the level of energy, although you may have a particle also with UDD, this particle also have an electric charge +1 because it charges the quark, but the mass will be very different from the mass of the proton, and they call it another particle. So we may have different hadronic states with a different combination of the quarks. We give different internal angular momentum states, what means different mass. So even with the same group of quarks, you may have them organized in a way that the mass is different, it's very, very different. So what's going to happen is that in the case, they will go together to a lower level, and that particle will decay until you get to the lowest possible level, that in most of the cases is going to be a proton. So hadron, the lightest one is a proton. If thing gets to a proton, that's it. Cannot, the same way as an electron cannot decay into anything, the proton itself cannot decay anything. There are some theories nowadays that people consider the possibility, but this is a theory. So far, the proton is stable, doesn't go down. Now, let's see example of decays involving hadronic states. Hadronic states that have quarks. No? For instance, we have a proton. The mass of the proton. In fact, the proton is UUD. You wrote it right. Eh? That's wrong. Let's fix this here before you. The proton is UUD. So the mass of the proton is 938.3. A neutron is UDD. If there is a small difference, so the mass, basically the mass of the neutron is a little bit bigger than the mass of the proton. So here we have a Feynman diagram of a process. Here we have a neutron. Neutron is UDD, got together. And what happens at some point here, exchange. What happens? So the quark D, at some point, the W changes its electric charge. So the quark D now is no longer a quark D, it's a quark U. If you remember from here, where is this? Here. See? D and U, they may exchange by the W. So in that case, at this point here, the D exchanges the W, so the D is no longer a D, but now it's a U. And then you had UDD, now you have UDU, so it's a proton. And this W, the W is carrying electric charge. Yeah? So at some point here, the W becomes an electron, and electron neutrino, the same way that it happens here. The same way. The W here is the same. The W doesn't care from where it comes from, right? So at some point here, so what you observe is that you start with a neutron, and at the end you have a proton, an electron, and the anti-electron neutrino. So the neutron itself decays into a proton. That's a lighter particle here. The loses one unit of electric charge, it becomes a U, and then the W turns into electron in the antineutrino electronic. So what you observe is so a free neutron, you have a free neutron, it decays to a proton. Quarks have a mass much bigger than quark U and quark D. So if you want to have a quark move up, you have to give energy to that quark. So naturally, it's not lose and decay. Okay? So now let's talk about the decay rate. We see that the particles will decay into particles of lower mass. But how that happens at what rate? So let's give here some examples. Okay? Well, the decay rate depends mainly of the interaction involved.
Sí, cayó de nuevo.
Oops.
Ya lo llamo, ya lo llamo.
Yeah.
Can you hear me now again?
Sí.
Ya, ya.
Ah.
Sí, Helio.
Yeah. Okay. Where have we stopped?
If you share your presentation, maybe I can tell you.
Okay. Let me start again.
From slide 2, maybe.
And like to maybe great. So let's share. Okay. Can you see my screen?
Yes. Yeah, that's right.
Okay.
That's the one. Perfect.
Okay. So I didn't miss much. Okay. So now let's see this decay. We're talking about this part that's the hole zero. Hole zero is a meson. So has a meson. Has a quark U and an anti-quark U. Okay? No charge. Because U and the anti-U has opposite charge. Okay? So what happens here? At some point here, exchange a gluon. Okay? So the anti-U exchange a gluon, but the gluon does not change the flavor. So the anti-quark U is still anti-quark U, no change. Okay? Here. Now, at some point after, this gluon turns into a D, anti-D. A D anti-D. Then at the end we have another meson. And here we have another meson. We call those meson pi, a pion. So we start with a hole, 0. At the end we have two other mesons, a pi mass, pi plus, and a pi minus. See, at the beginning the electric charge was 0, at the end the electric charge is 0. But you no longer have the whole 0. Now we have two particles, pi plus and pi minus. No? Okay. But here, notice that you may have the same process. But in that case, the anti-U exchange photon. So electromagnetic. Here, in this case, is strong. Here is electromagnetic. And this gamma, at some point, also materializes into a D and a D bar, like before. And again, we have the same way, rho 0, go into pi mass, pi. So you may have this process of this decay process happening by strong interaction, a strong process, or by an electromagnetic process. Yeah? We mentioned before that the strong process is much stronger, as the name suggests. So what happens is that the stronger process dominates. Although both cases may have, is a strong process that will prevail. So stronger the process involved, faster it may happen. So the strong dominates the electromagnetic, dominates the weak. So in case we may have two of them happening, or maybe three of them happening, at some point, the strongest will prevail. If you have a process that only goes through the weak interaction, the process is weak, it will be long. So basically, particles that decay, in the decay process, is involved in a weak process. It takes much longer for the process to happen. When the process is strong, the process is fast. It happens fast. Here is a table that gives some idea. For instance, here we have a particle that we call delta. Delta, né? Delta. We have the whole. We have omega. Here I have another particle called J psi. What happens to those particles, the decay delta, the dominating process is a strong process. And here you see an idea of how long the particle lives. The lifetime means how long does the particle lives. Once you produce a delta, for whatever means, how long does the process lives? So you see that the delta typically lives 10 to minus 24 seconds. So very short lifetime. But if you go to a particle, here we have pi 0, we have a sigma 0, so three other particles. The process of the decay process of those particles is basically an electromagnetic process. So it's a process that's slower than the stronger process. So they decay, their life is much, since the delta lives at about 10 to minus 24, this particle lives at 10 to minus 18. It's a very small number for us, but 10 to minus 18 is much, much bigger than 10 to 9 to minus 21. So 1,000 times bigger. So this particle lives longer, so the decay process is lower. And then here we have a bunch of particles that decay basically for a weak process. Notice that they live much longer than the other particles. The neutron here has a lifetime of the order of 1,000 seconds. The others are smaller, but all much bigger. All much bigger than the strong. So one idea for us to know what process is involved is to see how long does it happen. Very short lifetime, only the decay producers are observed. Because if the particle does not live long enough, you don't see that part. You produce a delta, and the delta decays very fast. You produce a hole, and the hole decays very fast. So you cannot see that part. You only see what they produce. But particles like the moon or the cown, is a cown, moon. They live long enough for us to observe. So if you're in a laboratory and if you produce a cown or a moon in the laboratory, it lives long enough for us to observe that particle. But particles that decay, basically the process involved a strong process, they live so short, they're so fast that you cannot see the particle. You only see the results of the decay. Opa. Okay. That ends basically the basic introduction I want to do today. Let me see. What time is it now? Because we still would have 15 minutes. Okay. Not enough time to 15 minutes, right? We waste some time today where things start working. So, but there are a few things that I want to show you. Let me see if I have here. Wait a minute. Onde está isso aqui? Onde está isso aqui? Eu não vou achar agora. Que coisa? What strange, coisa particular, download. I think I have to. Okay, I will make a drawing. Let me. You are still sharing my screen, right?
Yep.
I'm going to show very briefly a few Feynman diagrams and see what we can talk about those Feynman diagrams. For instance, let me see this Feynman diagram here. A basic Feynman diagram. Okay? And here, let me see this Feynman diagram here. Okay, two Feynman diagrams. See, which of those two Feynman diagrams is a possible Feynman diagram which one is not? If you observe the Feynman diagram, here in the case we have, sorry, where is this here? Here we have an electron, exchange, here we have electron. Here we have, again, here we have a neutrino. Okay, an electron has electric charge, so an electron can exchange a neutrino. My goodness. A neutrino, on the other side, does not have an electric charge. So it's not possible for a neutrino to exchange an electron. So this Feynman diagram here is not possible. Because only particles with charge, electric charge, may exchange photon. Another electron is this one here. Let me see. I made it, this a photon, a photon, a photon, and a photon. Okay, and I may have this Feynman diagram. Here I have a D. I have a D, a T, and here I have a W. Okay? Well, let's see these two situations. Are those diagrams possible? No, both are not possible. Okay. Here we have a photon. The first way we have a photon. Here, exchange. Well, only particles with electric charge may exchange a photon. And the photon has no electric charge. So this thing here is not possible. Now, here what we have a quark D, and we have a quark T. Okay? Is that possible? Look, here, what you have here is that exchange a W. And here we have T, basically, D, T. Yeah? Is it possible to have a thing like that? Listen. The W takes electric charge. So when the particle sends a W, it loses a charge that goes with the W. And when the particle receives the W, it gets that electric charge. So the charge between the quark D and the quark T, there is a difference of 1 electric charge. So it's possible to go from D to T. The W will provide the difference in charge. Let's see this one here. I have here mu, a mu, and a glue. This is a possible Feynman diagram. I can listen. I may draw whatever Feynman diagram I want, but it doesn't mean that it has physical meaning. So it must take care of all laws of physics. When they're going to make a calculation of Feynman diagram, it will be impossible. It will be necessary to take in consideration conservation of energy, conservation of momentum, conservation of charge, many other conservation laws. In this case here, we have mu at the top. Here we have exchange of gluon. Only particles that have a strong color charge, so only particles that participate in the strong interaction can exchange gluon. Muons do not have a color charge. Muons cannot participate in strong interaction. So a muon cannot receive or send a gluon. So this one is also not possible. Okay? So I can go ahead and produce many different plots. So just one more example. I may have here a neutrino. Let's say a neutrino do tau. Have another neutrino do tau here. And then here I have a Z. Is that a possible diagram? Well, what you have here? You have neutrino. And here you have the exchange of Z. This Z does not have electric charge. Neutrino, Z acts only the weak interaction. Neutrinos have the weak charge, whatever that is. So a neutrino can exchange a Z. A neutrino can send a Z, can receive a Z. So in this case, it's possible. Note that neutrino is still the same. You have a neutrino. Oh. Now, if the neutrino were changed, I cannot have things like this. Let's now see if I have an electron. Here I have neutrino, and here we have a W. Is that possible? Well, here we have the exchange of a W. The W has electric charge, so when some particle receives or sends a W, it loses electric charge. So here we have an electron, and here we have a neutrino. And indeed, the electron now sends a W and becomes a neutrino. However, here nós temos this is a muon neutrino. And this is an electron. This is not possible. An electron, if you remember the family that I showed, the family is electron, electron neutrino, muon and the muon neutrino, tau and the tau neutrino. So if an electron loses the electric charge through a W, it goes to an electron neutrino. So this thing here is also not possible. We cannot change the family from the electron. We cannot go from the family from the electron to the family from the muon, from the family from the tau. This is not possible. Remember from the diagram that I showed from muon decaying, the muon sent a W and then became an muon neutrino, and then the W became an electron and an anti-electron neutrino. So again, we have electron neutrino together with an electron. We have electron neutrino together with an electron, and so on. So that's what I have to present today. And tomorrow we're going to make some presentations, and eventually we have to have some knowledge about some quantum mechanics and some knowledge about relativity that we need to make some calculations on some Feynman diagram. So we'll do that tomorrow. I hope that tomorrow the system is more stable than today. But again, I think it works. Any questions, comments?
Yes, if I may.
Let me see.
This is Andres.
Okay. How are you doing?
Professor Motta, a couple of questions. when you were
Okay.
when you are describing the, can you hear me?
Yes, I can.
Yeah, when you were describing the interaction with the particles, one makes equivalent the electromagnetic interaction and the weak interaction. That's question number one. The second one was what gives stability to the particles? Why the large particles are more unstable than the other ones? And based on these two, I just venture to guess that the electromagnetic and the weak interaction.
Drop. I reconnect. Wait a minute. I could not because. Hello.
Hello, yes, I can hear you.
Hello. Wait. The connection dropped. I could not hear. Yes, and now because I reconnected, so I cannot hear your question. I have to restart. I'm sorry.
Oh, okay. I have two questions.
Hello.
Hello, yes, I can hear you. Yes.
Okay, I have to do it again because. Okay.
Okay.
Go.
First question. What makes
Go ahead.
Okay, what makes equivalent the electromagnetic interaction and the weak interaction? And the second is why the more heavy particles, what determines the stability or lifetime of a particle?
Give me a paper. Listen, the stability of I was not in the committee that designed the universe. Okay, so because special. So unfortunately, I would have done it different. So many of the things we really do not know, but basically, what defines the stability of a particle is that if there is nothing below the system, the universe is all the same. Okay? All things go to the lowest level of energy. That's what happens if I get this. If I get my cell phone here and if I let it go, it drops because it goes to stop at the floor. If my hand was not here to hold it. So the same happens to particles. If the particle is a combination of all the fundamental particles. And what people understand today, this comes from a field, but then we have a particle with some level of energy. If there is something below that level of energy, that particle will go, that particle, now it's more time to sell something. No. So if there is something below, it's a lower level of energy, that particle, that system, understand the particle system go to the lowest possible level. It's a particle, like a muon. And below that particle has another one, that's an electron. That's the lowest level of energy, the muon will drop, same way that my phone, that will drop to floor. And its floor will be the neutrino. When it gets there, there's nothing below. Mm-hmm. The other question about the lifetime, right?
Yes.
So the stronger process happens faster. So if you have a particle, a process to go into the strong interaction, it will happen much than the process that goes through the electromagnetic interaction. It's just a characteristic of the process itself. The strong interactions are strong. They really take over the thing. It happens. They don't wait for things to happen. And the weak interaction, as we mentioned before, is basically connected to the probability of that thing happening, the probability of changing a group, the probability of changing W. So if the probability of changing a group is much higher for exchanging W, because the strong interaction, then the process that requires to exchanging a group will happen faster because the probability is much higher than the other one. So that's basically what explained because of the process, the time is different. But there are details that I really cannot explain because it's very complicated.
All right. Thank you.
Okay.
Someone asked for a bibliography. Okay. I will send a bibliography tomorrow.
Okay. There is another question here. It says, does the neutrino oscillation can be described by Feynman diagrams?
Just a moment. Can you see this book?
Yeah, the Mark Thompson.
Okay, I sent a list of 2 books. The book, the question is if neutrino oscillation can be described. Okay. Neutrino oscillation is another subject. I was not planning on talking about neutrino oscillation, but neutrino oscillation has a problem. Maybe not a problem. In neutrino oscillation, we have a mu neutrino, and this mu neutrino at some point shows up as electron neutrino. I have just said a few minutes ago that that's far better. We can have an electron going to a muon neutrino. The electron goes to a electron neutrino. However, a muon neutrino, an electron neutrino, may oscillate into a muon neutrino. So at some point, it will be possible for you to observe the oscillation. But in principle, the Feynman diagram does not show that. And the Feynman diagram does not show this process because the oscillation of the neutrino is connected to what's called a mixture. It's a quantum phenomenon that's I'm not going to talk about. But what you see as a neutrino is not a neutrino. It's a combination of 3 states, like that people want. So this quantum combination can produce what we call oscillation. That also happens to quarks, by the way. So no, we don't have a Feynman diagram showing the oscillation. I look around to see if there is a way to describe this, but not through Feynman diagrams. Sorry.
Okay, thanks, Helio. Is there any other question?
Okay. I sent the bibliography. I sent the bibliography to Professor Castromont, and then I do not know how he distributes that. But anyway.
Okay, thanks.
Okay.
Thank you. Okay, Helio. Well,
so how can I send it distribute? It's up tomorrow.
Okay.
See you if the connection helps.
He just left. Salió Helio. Bueno, si no hay alguna otra pregunta, escríbanlo en el chat, por favor. Sí, Helio se puso, algo pasó, su conexión está bastante, inestable. Hablando de inestabilidad, ¿no? Sí, por favor, pueden escribir acá en el chat, que yo lo estoy anotando, estoy capturando, y mañana, cuando comencemos, le hago las preguntas rápidas o que las conteste al inicio, ¿no? O las dejamos para el final y así vamos, o sea, que no se pierdan las preguntas. ¿Ok? Entonces, o lo escriben por el chat o lo escriben por el correo electrónico. Una bibliografía, justo Helio dijo que va a pasarme la bibliografía que él está usando. Uno de los libros que él está usando es el Modern Physics de Mark Thompson, es un libro, digamos, relativamente nuevo. Proton Decay. Modelos de gran unificación, sí es posible. En lo que nosotros tenemos, en modelo estándar, no. Los PDFs. Mark Thompson, sí. Estoy anotando acá. Voy a hacer la pregunta respectiva a Helio. Estoy anotando acá. ¿Ok? Ok. Si hay alguna otra pregunta, duda, comentario. Si no, bueno, les agradezco a todos por su participación y nos estamos viendo nuevamente mañana a la misma hora, ¿ok? Ok. Helio justo me está diciendo, me va a pasar la lista de la bibliografía y yo se las voy a pasar a ustedes. O lo vamos a disponibilizar mejor en el site, creo que es más adecuado, ¿ok? Para todo el mundo. Nuevamente agradeciéndole su participación, cerramos la transmisión por hoy día, ¿ok? Continuamos mañana a la misma hora, 2 de la tarde, ¿ok? Muchísimas gracias a todos ustedes. Tengan muy buenas tardes, ¿ok? Cuídense, por favor, ¿ok? Hasta mañana.